Okay, so now let's go back to baseball and or softball. It could be either way. So a pitcher throws a curveball by putting spin on the ball. A simple model assumes the spin produces sideways acceleration. Obviously, this can get much more complicated, but that's what we're going with just for our beginning problem. So it's perpendicular to the horizontal and vertical components of the pitch. So we've got a sideways spin. So suppose that a pitcher throws that curveball with initial velocity 130, 0, negative 3 from an initial position of 0, 0, 6. If the spin provides sideways acceleration of 8 feet per second squared, how far off center will the ball be when it reaches home plate? Okay, so let's think here. So we have a pitcher throwing the ball. Now, the way the ball is thrown, it starts off at an initial position, which we can write here, initial position, which is x0, y0, z0 of, that's a 0, of 0, 0, 6. Right there, initial position. So it's going to start up here, and then it's going to get thrown out, and it's going to have a spin, and it's going to end up over here. Right? So it's arcing. I probably do that arc too arced, but that's okay. All right, so home plate is over here, right? So over here is home plate, right? And they're trying to get the person standing at home plate to swing, essentially. Okay, so let's think here. Let's start with acceleration. So the acceleration would be, again, 0, comma, and then they have a spin in the y direction of 8 feet per second. Right here. So they provides acceleration 8 feet per second. All right, so that'll give us 8 right here. And then we always have gravity. Now, this is in feet, so let's make a note. Gravity would be negative 32. Well, actually, it's negative g, but positive. Anyway, here, I'll just write 32. 32 feet per second squared. We just always assume, I was about to write feet per second, which is also correct, but feet per second squared. The way it always works is it's always negative because gravity is always pulling us down. So either you think of gravity as negative over here, or you just remember to put it in here. So either way you like it, right? Gravity is going to be pulling you downward. So you can put the negative here or put the negative there or both. It's fine. Okay, so we have acceleration. Now keep in mind this would be feet per second squared. This is because of the curve, and this is because of gravity. All right, I'm not going to circle that because that's not what they wanted, but I'm working on it. So, all right, then what about velocity? Velocity would be the integral of acceleration with respect to time. So that's the integral of 0, 8, negative 32 with respect to time. And that would be 0, 8t, negative 32t, plus your initial velocity, right? But I know my initial velocity. It's right here, right? It was given to me in the problem. So I'll just write that down here. Initial velocity is 130, 0, negative 3. That would be feet per second. This is u0, v0, w0. It's just the letters we use. Okay, so this is 130, 0, negative 3. All right, therefore velocity is 130, 8t, negative 32t minus 3. There's velocity, and that would be feet per second. All right, so I have velocity, I have acceleration. But I think we need to go further and find position because the question is asking how far off center. Far is distance. So I'm going to need position to be able to answer this question. All right, so let's find position. Position is the integral of velocity with respect to time, and that would be the integral of 138t negative 32t minus 3 with respect to time, and that would be 130t 4t squared, because we add 1 to the power and divide, negative 16t squared minus 3t plus some constant vector. And that constant vector would be initial position, which was 0, 0, 6. Therefore, position is 130t, 130t plus 0, so just 130t, 4t squared, and then negative 16t squared minus 3t plus 6. And that'd be feet. Oh, I shouldn't have circled that. That wasn't the answer. Hold on. I only meant to underline it, so let me underline it. Okay, so I've given myself just a little bit of room here to figure out the answer to the question, which is how far off center will the ball be when it reaches home plate? Well, to do that, we're going to need to know how far away it is. So I just Googled this, right? The distance from the pitcher to the home plate, of course, it varies a bit from where the pitcher stands and stuff, but we're going to go with the mound to home plate is a distance of 60 feet, 6 inches. So that'd be 60.5 feet. Okay, so distance to home plate would be in the x direction. So it'd be x equals 60.5 feet, right? 60 feet, 6 inches. Great, so we're going to set the x equal, right? Because it's going out this way. So you're trying to figure out, like, how far out this is this, right? Home plate from the pitcher's mound to here is 60.5 feet, right? Comma 0, comma 0. That's where home plate is standing. All right, so 60.5 equals 130t. And then we solve that for t. Divide by 130. All right, so hey Maple, take 60.5 and divide it by 130 for me. So 0.4656. So 0.4656 seconds. So this is when it hits the ground, or excuse me, when it reaches home plate. But we want to know how far off center. That's in the y direction, right? We know what the z is going to be. The z is going to be 0, right? So how far off center would be to find the y at that time, 0.4656. So we would take 4 times 0.4656 squared, which we can do in Maple pretty easily. 4 times that answer, so insert label, give me the answer 6.1, and square it. So we're off 0.866 feet. Not quite a foot, just a little bit. 0.866 feet off. Okay, so what makes a curveball so difficult to hit? What's going on here? So when the pitcher throws it, it seems like it's coming towards the batter. So the batter swings and it arches away. Why is that happening? Well, let's look at the spin in just the y direction. So let's take a moment and think about the y of t, which was 4t squared. We know what that looks like. That's a parabola, right? So it's a parabola that goes this way. So this will be t time, and this is y. Okay, so in the first, and then we'll say that it lands at, what was it, 0.4656. So let's say right here is where it reaches home plate. So that is, the time is 0.4656 seconds. Okay, so this is the time of the flight, right? Time of flight. So when the ball first leaves the pitcher's hands over here, the first half of the pitch, this would be like this, right? So here's the first half in terms of time. So the first half of the pitch as the ball is sailing, so the first 0.25 seconds, you can see that there's not a lot of curve there, right? It's kind of close to what a straight line would be. Not perfect, but, right? There's not a lot of concavity is what I want to say, right? It's not a lot of arch to it. I have to find my whiteout here. Right? The arch is not significant. So in the first half, not a lot of concavity. I'll just say arch. No, I can't handle it. Or concavity. Right? It's not very concave. But what about the second half? Let's look. So the second half of the flight, as it approaches the batter, and keep in mind this is all happening in less than a half of a second. So as it approaches the batter, gets closer and closer to the batter, right? Then, which this is the time when it reaches home plate, if you will. So as it gets closer, it's arching more. There's more concaveness, right? So, and you can see how much more arch, how much longer that is to this little piece too, right? There's more of the curve in there. And that's why it's so hard for a batter to kind of understand what's happening and be able to swing and hit it. Of course, they've done a lot of studies that batters actually don't look. For the most part, they just swing. It's very, very, very hard for them to figure out what's going on in their brain because it's happening too fast. So more of the curve, right? Literally more of the curve part is in the second half. Second half of the flight, which is closer to the batter, and that's why the batter swings. And misses because it arches away from them just in time.